On the moon, a feather and a hammer dropped simultaneously hit the ground at the same time. In 1971, Apollo 15 astronaut David Scott conducted a simple but powerful physics demonstration on the surface of the moon. Before we continue, consider subscribing and leaving a like, small actions that help keep the signal flowing through the noise. So, holding a hammer in one hand and a falcon feather in the other, he dropped them simultaneously. To anyone watching on Earth, it was a surprising sight. Both objects hit the lunar surface at exactly the same time. On Earth, that would be impossible because air resistance slows lighter objects, like feathers, significantly more than heavier ones. But the moon has no atmosphere, no air molecules to resist motion, so objects fall purely under the influence of gravity. This lack of air resistance allowed the hammer and the feather to accelerate at the same rate and land together, exactly as predicted by Galileo over 300 years earlier. He theorized that in the absence of air, all objects, regardless of their mass, would fall at the same rate. This principle, known as the equivalence of inertial and gravitational mass, is a foundation of Newtonian physics and was later incorporated into Einstein's theory of general relativity. On Earth, demonstrating this is nearly impossible without a vacuum chamber, but the moon's natural vacuum created the perfect environment. The gravity on the moon is about 1/6 that of Earth, so objects fall more slowly, but the uniformity of acceleration remains. The Apollo 15 demonstration provided a stunning, visual confirmation of a fundamental truth in physics, using nothing more than a hammer, a feather, and a vacuum of space. It stands as one of the most iconic experiments in scientific history. There's a giant cloud of alcohol in space, Sagittarius B2, containing enough ethanol to make 400 trillion pints of beer. In the heart of our galaxy, near the center of the Milky Way, lies a vast molecular cloud known as Sagittarius B2. Spanning over 150 light-years, this immense region of gas and dust is notable not only for its size, but for its chemistry. Astronomers studying its spectral emissions discovered an astonishing fact. It contains billions of liters of ethanol, the same type of alcohol found in alcoholic beverages. The cloud's ethanol content is staggering, estimated to be enough to produce 400 trillion pints of beer. This alcohol isn't floating around in liquid form. Instead, it's dispersed as gas, with molecules formed through complex chemical reactions on icy dust grains in deep interstellar space. Ultraviolet radiation, cosmic rays, and extreme cold, temperatures just a few degrees above absolute zero, all contribute to the formation and release of organic compounds in such regions. Ethanol is just one of over 70 complex molecules detected in Sagittarius B2, including amino acids, esters, and even simple sugars. These discoveries suggest that the basic building blocks of life are widespread throughout the galaxy, possibly even common. Sagittarius B2 serves as a natural laboratory for astrochemistry, where the interplay of stellar radiation and interstellar dust drives the formation of increasingly complex molecules. Though it's located about 390 light-years from the galactic center, it provides a fascinating glimpse into the organic richness of the cosmos. While we'll never distill beer from it, Sagittarius B2 tells us something profound. The ingredients for life are not only earthbound, they're scattered across the stars. On Titan, you could fly by flapping your arms. Its thick atmosphere and low gravity make it possible. Titan, Saturn's largest moon, is one of the most fascinating bodies in the solar system, especially because of its thick atmosphere and low gravity. The atmospheric pressure on Titan's surface is about 1.45 times that of Earth's, meaning it has a denser atmosphere than any other moon and even some planets. Combined with its weak gravity, only about 14% of Earth's, this creates conditions where human-powered flight is theoretically possible. If you wore a wingsuit and flapped with enough force, you could lift off the ground and glide through the dense nitrogen-rich air. On Earth, human-powered flight is extraordinarily difficult because the air is too thin relative to our weight. But on Titan, the increased buoyancy from the dense air and the lower gravitational pull would give a human, with wingspan assistance, the ability to become airborne. The moon's cold temperatures, averaging minus 290 degrees Fahrenheit minus 179 degrees Celsius, and lack of breathable oxygen would still require full environmental protection. But from a physics standpoint, the concept of flying like a bird is plausible. This makes Titan the only body in the solar system where unassisted aerial movement by a human might be feasible. The interaction between atmospheric density and gravity has never aligned so favorably elsewhere. Titan's sky would offer a unique horizon, with a golden haze and methane clouds swirling overhead, making it not just a scientific wonder, but a surreal setting for theoretical flight. It's an extraterrestrial environment where humans could literally take wing, if only for a few moments. The moon was once part of Earth. It was blasted off by a collision with a Mars-sized protoplanet, Theia. The prevailing theory about the moon's origin is the giant impact hypothesis, which suggests that around 4.5 billion years ago, a Mars-sized body named Theia collided with the early Earth. This colossal impact ejected an enormous amount of debris into orbit around our planet. Over time, this material coalesced due to gravitational forces, forming what we now know as the moon. The evidence supporting this theory is substantial. The composition of lunar rocks collected during the Apollo missions is strikingly similar to Earth's mantle, particularly in isotopic ratios of oxygen and other elements. This similarity implies a shared origin. Additionally, the moon's lack of a large iron core compared to Earth suggests that much of the material that formed it came from the outer layers of Earth and Theia, not their dense centers. Simulations of planetary formation support the physics of such an impact, showing how debris could settle into a stable orbit and gradually merge into a single satellite. The impact also helped shape Earth's axial tilt, and might have influenced the development of our seasons. Without the moon, Earth's climate and biological evolution could have followed a dramatically different path. This ancient collision was a violent, but ultimately stabilizing event. The moon's formation represents a key turning point in the history of the solar system, tying Earth's evolution to cosmic-scale events, and reminding us that planetary bodies are shaped not just by gravity and time, but by immense and chaotic collisions in the universe's early days. Venus spins backward. Its sun rises in the west and sets in the east. Venus, the second planet from the sun, has one of the most unusual rotations in the solar system. Unlike most planets, it rotates in the opposite direction of its orbit, a condition known as retrograde rotation. On Venus, the sun would appear to rise in the west and set in the east, completely opposite to what we experience on Earth. Moreover, Venus rotates extremely slowly. A single day on Venus, one full rotation on its axis, takes about 243 Earth days, making a Venusian day longer than its year, which lasts about 225 Earth days. The cause of Venus's strange rotation is still a matter of scientific debate, but theories include massive collisions with other planetary bodies during its early history or gravitational tidal interactions with the Sun. Venus's thick, toxic atmosphere, composed mostly of carbon dioxide and clouds of sulfuric acid, adds further complexity. The planet's surface pressure is over 90 times that of Earth's, and its cloud tops move faster than the surface itself, a phenomenon called superrotation. Despite its similarity in size and composition to Earth, Venus is one of the most hostile environments in the solar system, with surface temperatures hot enough to melt lead. Its retrograde spin, combined with its hellish conditions, makes it a planetary outlier, an example of how dramatically different two seemingly similar worlds can become. Venus challenges assumptions about planetary formation and evolution, offering both a cautionary tale and a mystery still being unraveled by planetary scientists. Astronauts smell like seared steak after spacewalks, due to chemical reactions on their suits. After a spacewalk, when astronauts return to the International Space Station and repressurize the airlock, many report an unexpected and consistent odor clinging to their suits. described as smelling like seared steak, burnt metal, or welding fumes. This phenomenon is not caused by the vacuum of space itself. Space has no air and therefore no smell, but rather by the interaction of high-energy particles and atomic oxygen in low Earth orbit with the materials on the astronauts' suits. When exposed to this harsh environment, materials in the suits or on the surface of the ISS may undergo a form of oxidation or chemical change. Once back in the station, the returning suit is exposed to normal atmospheric conditions, allowing volatile compounds created during exposure to react with air molecules and reach the astronauts' noses. The result is a pungent, metallic, and smoky aroma, one that is both consistent and distinctive. This smell provides indirect evidence of the unique and reactive nature of the space environment. It's a reminder that even without an atmosphere, space is far from empty. It is filled with energetic particles, micrometeoroids, and atomic oxygen, especially in low Earth orbit, that can corrode and chemically alter surfaces. While it may seem like a trivial detail, this scent is a sensory window into the extreme conditions of outer space, where radiation and atomic interactions shape not only what astronauts see, but even what they smell. The space smell is an artifact of space chemistry, etched into their gear. Mars has lava tubes up to 60 kilometers long, potential shelters for future colonists. Beneath the dusty surface of Mars lies a network of ancient lava tubes, vast, hollow tunnels formed by flowing molten rock during the planet's volcanic past. Some of these tubes stretch for up to 60 kilometers in length and could be dozens or even hundreds of meters in diameter. When surface lava cools and solidifies while the molten lava beneath it continues to flow, it can leave behind empty channels, tubes that remain structurally stable for millions of years. These Martian lava tubes are of intense interest to scientists and engineers because they offer natural protection against many of the hazards of the Martian surface. Radiation is a major concern on Mars, where the thin atmosphere and lack of a global magnetic field allow cosmic rays and solar radiation to reach the surface with little shielding. Lava tubes, buried beneath rock, could act as shelters for human explorers, shielding them from this radiation, as well as from micrometeoroid impacts and temperature extremes. The internal environment of a tube would also be more thermally stable compared to the surface, where temperatures can swing wildly from day to night. These natural structures could serve as ready-made habitats for future Martian colonies, needing only to be sealed and pressurized. Moreover, they could preserve evidence of past microbial life, having been protected from the harsh surface conditions. Mars lava tubes offer both a potential refuge and a scientific treasure trove, making them prime candidates for future robotic and human exploration missions. The solar system zooms around the Milky Way at 514,000 miles per hour, 828,000 kilometers per hour. Our solar system isn't stationary. It's in constant, rapid motion as it orbits the center of the Milky Way galaxy. The entire system, including the Sun, planets, moons, asteroids, and comets, travels at an astonishing speed of about 514,000 miles per hour, or 828,000 kilometers per hour. Despite this immense velocity, we don't feel it because space is essentially frictionless, and everything around us is moving together at the same speed. The solar system takes approximately 230 million years to complete a single orbit around the galactic center, a journey often referred to as a galactic year. This orbit isn't a perfect circle, and the system also bobbles slightly above and below the galactic plane as it moves, influenced by the gravitational pull of other stars and dark matter. The gravitational center it orbits is thought to contain a supermassive black hole, Sagittarius A*, which anchors the Milky Way's rotation. Although the galaxy looks static from Earth, this high-speed orbit contributes to the dynamic evolution of stellar systems and influences cosmic ray exposure, interstellar gas interactions, and the long-term structure of the galaxy itself. Our rapid motion through space also means we are constantly moving through different regions of the galactic environment, which may affect everything from the shape of the heliosphere to potential cosmic threats like passing stars or molecular clouds. This immense journey underscores how deeply embedded Earth's fate is within the grander dance of the galaxy itself. Water and microgravity can spontaneously combust. NASA experiments. In microgravity environments like the International Space Station, fluids behave in ways that defy everyday experience on Earth. One striking observation from NASA's experiments is that water, typically a suppressant for fire, can behave in ways that are surprisingly volatile under certain conditions. While water itself doesn't ignite, experiments have shown that fuel droplets in microgravity can burn more slowly, and in some configurations, combustion can occur even inside water droplets. In one such case, a fuel droplet suspended inside a water bubble ignited and continued to burn, an event practically impossible on Earth due to buoyancy-driven convection. In space, combustion is not driven by rising hot gases because there's no up. Flames form spherical shapes, burn at lower temperatures, and can be sustained longer in microgravity, depending on fuel and oxygen availability. In rare cases, this can make fire more difficult to detect and extinguish. Water in microgravity tends to form floating spheres due to surface tension, and these can encapsulate gases or flammable substances. If the right chemical mix is trapped inside a water sphere, such as certain alcohols or hydrocarbons, ignition is possible when exposed to a spark. This unexpected behavior has important implications for spacecraft safety, life support systems, and fuel storage. NASA continues to study combustion in space to better understand fire behavior in microgravity, aiming to design safer systems for future missions. The lesson is clear. Even a familiar substance like water can behave unpredictably in space, and understanding those changes is crucial for survival beyond Earth. Neutron stars have mountains just 5 millimeters tall, but they weigh more than Everest. Neutron stars are the remnants of massive stars that have undergone supernova explosions and collapsed under their own gravity. What's left is an object so dense that a single teaspoon of its material would weigh billions of tons. On such an extreme surface, gravity is so powerful that it flattens almost everything into perfect uniformity. Yet these stars can have mountains, slight protrusions no more than 5 millimeters tall. Despite their tiny size, these neutron star mountains are the tallest structures such surfaces can support. The pressure and gravitational pull are so immense that anything higher would collapse under its own weight. But the fascinating part lies in their mass. These millimeter-high features can weigh more than Mount Everest, which on Earth reaches a height of 8.8 kilometers. That's because density on a neutron star reaches around 101710 17 kilograms per cubic meter, equivalent to squeezing the mass of the sun into a sphere just 20 kilometers wide. These tiny deformations are not just theoretical curiosities. They play a significant role in gravitational wave research. If a neutron star rotates with a slight imperfection, like a mountain, its asymmetry can emit ripples in space-time. Advanced detectors like LIGO are searching for these gravitational waves, which could confirm the presence of neutron star mountains and provide insights into the internal structure of these ultradense objects. In the context of stellar physics, neutron star mountains are a reminder of how extreme the cosmos can be, where the tiniest bumps hold unimaginable weight and cosmic significance. Saturn could float in water. Saturn, the sixth planet from the Sun, is a gas giant composed primarily of hydrogen and helium. Despite its enormous size, over 9 times wider than Earth, Saturn is remarkably light for its volume. Its average density is just 0.687 grams per cubic centimeter, which is less than the density of water, measured at 1 gram per cubic centimeter. This means that if there were a body of water large enough to contain it, Saturn would theoretically float. Of course, such a scenario is physically impossible, as there is no ocean vast enough to hold an entire planet. Still, the comparison offers a useful way to illustrate just how low Saturn's density really is. Its low mass-to-volume ratio results from its composition. Lightweight gases dominate its structure, and there's no clearly defined solid surface. The atmosphere becomes denser with depth, gradually transitioning into a fluid interior under high pressure, but the planet never forms a rigid boundary like Earth's crust. Saturn's density also affects its behavior. For example, its fast rotation, completing one spin in about 10.7 Earth hours, causes it to bulge at the equator and flatten at the poles. Its unique ring system, composed of icy particles and rocky debris, adds to its visual distinctiveness, but not significantly to its mass. Understanding Saturn's low density provides insight into how gas giants form, how their atmospheres behave, and how dramatically different planetary bodies can be from our Earth-based expectations. Cosmic rays make astronauts see flashes, high-energy particles hitting their retinas. Astronauts in space often report seeing unexpected flashes of light, even when their eyes are closed or the cabin is dark. These flashes are not hallucinations, but are caused by cosmic rays, high-energy particles originating from the sun, distant stars, and other astrophysical sources. When these particles strike the retina, they can interact directly with the cells in the eye or with surrounding tissues, stimulating a visual signal that the brain interprets as a flash of light. The phenomenon, known as phosphenes, was first reported during the Apollo missions and has since been confirmed by astronauts aboard the International Space Station. Cosmic rays are a mixture of protons, alpha particles, and heavier atomic nuclei traveling at near-light speeds. On Earth, we're shielded by the atmosphere and magnetic field, which absorb or deflect most of this radiation. But in space, especially beyond low Earth orbit, astronauts are directly exposed to higher levels of cosmic radiation. These rays can penetrate spacecraft walls and human tissue, posing risks to both short-term health and long-term mission safety. The flashes serve as an eerie reminder that space is filled with invisible, energetic particles constantly bombarding astronauts. Studying the biological effects of cosmic rays is a priority for space agencies, especially for missions to the Moon or Mars where exposure will be much higher. The light flashes in the eyes of astronauts aren't just curiosities. They are direct, perceptible evidence of a hostile, high-energy universe just beyond Earth's protective shell. Pluto has cryovolcanoes erupting ammonia and methane ice. Pluto, once classified as the 9th planet and now considered a dwarf planet, has turned out to be far more geologically active than previously imagined. When NASA's New Horizons spacecraft flew by Pluto in 2015, it captured detailed images of surface features that resemble cryovolcanoes, ice volcanoes. Unlike terrestrial volcanoes that erupt molten rock, cryovolcanoes erupt volatile substances such as water, ammonia, and methane in frozen or semi-liquid form. On Pluto, where surface temperatures average around minus 375 degrees Fahrenheit minus 225 degrees Celsius, these substances can behave like lava. Two major cryovolcanic structures were identified, Wright Mons and Picard Mons, both rising several kilometers above the surrounding terrain. These formations lack the impact craters that usually mark ancient surfaces, suggesting relatively recent geological activity. The presence of ammonia in the erupted material is particularly significant, as ammonia acts as an antifreeze, lowering the freezing point of water and potentially allowing a subsurface liquid layer to exist. If internal heat remains in Pluto's core, perhaps due to radioactive decay, it could drive this type of cryovolcanism. The idea of internal activity on such a small, cold world was unexpected and challenges assumptions about geological dormancy in the outer solar system. Cryovolcanoes may even play a role in transporting heat and materials from Pluto's interior to its surface. These structures provide evidence that Pluto, despite its distance from the Sun, remains a dynamic and evolving body. Cryovolcanism on Pluto not only reshapes our understanding of this dwarf planet, but also broadens the definition of what geological activity can look like across the solar system. On planet HD 189733b, it rains molten glass sideways at 4,350 miles per hour, 7,000 kilometers per hour. HD 189733b is an exoplanet located approximately 64 light-years away in the constellation Vulpecula. It's classified as a hot Jupiter due to its size, similar to Jupiter, and its extreme proximity to its parent star, orbiting once every 2.2 Earth days. This close orbit causes the planet to be tidally locked, meaning one side always faces the star while the other remains in darkness. The day side reaches temperatures of over 1,700 degrees Celsius, 3,100 degrees Fahrenheit, hot enough to vaporize various minerals in the atmosphere. Winds on HD 189733b whip around the planet at speeds up to 4,350 miles per hour, far faster than any hurricane on Earth. These winds carry vaporized silicates from the hot side into the cooler atmosphere, where they condense into tiny glass particles. What results is a sideways rain of molten glass, driven by supersonic winds across the planet's terminator, the dividing line between day and night. The high velocity of this glass rain means that if you stood in this environment, which is impossible, you would be sandblasted by scorching glass shards moving at hypersonic speeds. The planet also has a deep azure blue appearance, caused not by oceans, but by how silicate particles scatter blue light in the atmosphere. HD 189733b serves as an extreme example of atmospheric dynamics and chemistry on exoplanets. Studying such worlds helps scientists understand the range of conditions that exist beyond our solar system, expanding the definition of planetary weather into the realm of the violent and the surreal. Black holes ring, like bells, gravitational waves after collisions. When two black holes collide and merge, the resulting object doesn't immediately settle into a stable state. Instead, it enters a brief phase where it emits ripples in space-time, gravitational waves, similar to how a struck bell vibrates and emits sound. This phenomenon, known as the ring-down phase, is a direct consequence of Einstein's general theory of relativity. The merged black hole oscillates as it adjusts to its new mass, spin, and shape, and these oscillations radiate gravitational energy outward at the speed of light. Though the analogy of sound doesn't fully capture the nature of gravitational waves, the comparison helps illustrate how the structure of space-time itself behaves dynamically. The first direct detection of such waves was made in 2015 by LIGO, when two stellar mass black holes merged over 1 billion light-years away. The final ring of the newly formed black hole matched theoretical predictions exactly, confirming the validity of relativity in extreme conditions. These gravitational wave signatures are detectable only by incredibly sensitive instruments, capable of measuring distortions in space-time smaller than a proton. By analyzing the frequency and decay of the ring down, physicists can extract key information about the black hole's mass and spin, and even test for deviations from Einstein's equations. These cosmic rings are silent to human ears, but they carry profound information about the most energetic events in the universe. Each detection not only confirms theoretical physics, but opens a new observational window into the hidden workings of space-time and gravity. Jupiter has no solid surface. It's a swirling ball of hydrogen and helium. Jupiter, the largest planet in the solar system, is classified as a gas giant. It lacks a true solid surface like Earth's or Mars. Instead, it is composed primarily of hydrogen and helium, existing in gaseous form in the upper layers and becoming increasingly dense under immense pressure as you descend deeper into the planet. The outermost layer consists of colorful clouds of ammonia and water vapor, forming iconic banded structures and powerful storms such as the Great Red Spot, a massive cyclone that has raged for centuries. Below the visible cloud tops, the pressure and temperature increase dramatically, compressing hydrogen into a liquid state. Even deeper, hydrogen transitions into metallic hydrogen, a phase where it behaves like an electrical conductor due to the extreme compression. It's this metallic hydrogen layer that likely generates Jupiter's enormous magnetic field, the strongest of any planet in the solar system. The transition from gaseous to liquid to metallic states is gradual. There's no clear boundary where atmosphere ends and interior begins. If you try to land on Jupiter, you would simply sink through increasingly dense layers until being crushed by pressure and heat. The core may be rocky or icy and is possibly surrounded by a thick layer of metallic hydrogen, but it remains a topic of scientific investigation. Jupiter's structure demonstrates how dramatically different planets can be from Earth. It's a colossal, churning sphere without a surface to stand on, dominated by fluid dynamics and shaped by extreme pressure and chemistry. If you stood on a neutron star, you'd weigh billions of tons. A neutron star is the incredibly dense remnant of a massive star that has undergone a supernova explosion. When the outer layers of the star are ejected, the core collapses under its own gravity, squeezing protons and electrons together to form neutrons. The resulting object is typically about 20 kilometers in diameter, but contains more mass than the Sun. This extreme compactness means the gravitational pull at the surface of a neutron star is staggering, about 100 billion times stronger than Earth's. If a person weighing 70 kilograms stood on a neutron star, they would experience an effective weight of roughly 7 billion tons. The force would crush them instantly, even before they reached the surface, because tidal forces from the intense gravity would stretch and compress their body in a process called spaghettification. The surface itself is likely a thin crust of nuclear matter resting above a superfluid of neutrons and exotic particles, possibly including quark matter in the core. Time also behaves differently in such an environment. General relativity predicts that time near a neutron star moves significantly slower compared to Earth. Despite their size, neutron stars rotate incredibly fast, some up to 700 times per second, and emit beams of radiation, observed as pulsars when those beams sweep past Earth. Standing on a neutron star isn't just impossible, it defies the survival of matter as we know it. These stellar remnants are some of the most extreme objects in the universe, pushing the boundaries of physics and our understanding of matter under pressure. A day on Mercury lasts 176 Earth days due to its weird orbit-spin resonance. Mercury, the closest planet to the Sun, has one of the most unusual day-night cycles in the solar system due to its unique orbital and rotational relationship. Mercury rotates very slowly on its axis, once every 58.6 Earth days. However, it also orbits the Sun in just 88 Earth days. This results in a 3:2 spin-orbit resonance, meaning Mercury rotates 3 times on its axis for every 2 orbits around the Sun. Because of this resonance, a single solar day on Mercury, the time it takes for the Sun to return to the same position in the sky, lasts 176 Earth days. This strange timing creates extreme temperature variations. With no significant atmosphere to retain heat, Mercury's surface can reach 430 degrees Celsius (800 degrees Fahrenheit) during the long day and plummet to minus 180 degrees Celsius minus 290 degrees Fahrenheit during its extended night. Mercury's eccentric, egg-shaped orbit further complicates things, causing the Sun to appear to briefly reverse direction in the sky at certain points in its orbit. These dynamics are the result of early gravitational interactions with the Sun that locked Mercury into this rare rotational pattern. Studying Mercury's day length and orbital mechanics helps scientists understand tidal interactions and rotational evolution in planetary systems. It's also a reminder that a day is not a universal constant. It's shaped by complex relationships between a planet's rotation and revolution. On Mercury, time behaves in a way that would feel alien to anyone familiar with Earth's daily rhythm, where sunrise and sunset follow a much more predictable path. The universe might be a giant hologram, information encoded on its boundary. One of the most intriguing concepts in modern theoretical physics is the holographic principle, a hypothesis suggesting that all the information in the universe might actually be encoded on a two-dimensional surface, much like a hologram. In this view, the three-dimensional world we perceive could emerge from data stored on a distant boundary, perhaps the cosmological horizon. This idea originated from studies of black holes, particularly the realization that the amount of information a black hole can contain scales not with its volume, but with its surface area. Physicist Jacob Bekenstein and later Stephen Hawking showed that the entropy, or information content, of a black hole is proportional to the area of its event horizon, not its interior. Building on this, researchers propose that the entire universe could follow similar rules. The ADS/CFT correspondence, developed in string theory, provides a mathematical example of such holographic duality. In this model, a gravitational theory in a higher dimensional space, like a 3D universe, is equivalent to a non-gravitational theory on its lower dimensional boundary, like a 2D surface. While our universe isn't an anti-de Sitter space, the principle continues to influence cosmology and quantum gravity research. If true, it would mean that our perceived reality is a projection from a deeper, more fundamental layer of physics. This doesn't make the universe any less real, but it challenges our understanding of space, time, and information. The holographic principle remains one of the most fascinating and still unproven ideas about the nature of existence. Some planets are made of diamond, like PSRJ 1719-1438b. In 2011, astronomers discovered an extraordinary exoplanet orbiting the pulsar PSRJ 1719-1438, located about 4,000 light-years from Earth. What makes this planet unique is its composition. It is believed to be made largely of crystalline carbon, essentially diamond. The planet is what's left of a once massive star that lost its outer layers, leaving behind a dense core compressed under extreme pressure. This small, super-dense object orbits its host pulsar in just 2 hours and 10 minutes, indicating it's incredibly close and must be very compact to avoid being torn apart by tidal forces. The high density and carbon-rich nature of the planet suggests that much of it has crystallized into diamond-like structures. With a mass roughly that of Jupiter, but only a fraction of its size, the planet is denser than any known gas giant. Its proximity to the pulsar also bathes it in intense radiation, ruling out any atmosphere or surface life. These so-called diamond planets are theorized to form in binary star systems where one star siphons material from the other, eventually leaving behind a degenerate core of carbon and oxygen. Under enormous pressure, these materials crystallize. While it's not the shimmering, gem-like world one might imagine, the planet is a fascinating example of how exotic planetary compositions can be. The discovery of diamond-rich worlds like PSRJ 1719-1438b expands our understanding of planetary formation and shows just how extreme and varied the conditions in the cosmos can be. The sun doesn't burn. It's a nuclear fusion reactor, not fire. The sun shines not because it's on fire in the traditional chemical sense, but because it generates energy through nuclear fusion. At its core, where temperatures reach about 15 million degrees Celsius and pressures are immense, hydrogen nuclei are forced together to form helium. This process releases enormous amounts of energy, as a small fraction of the hydrogen's mass is converted directly into energy according to Einstein's equation, E equals mc squared. Unlike combustion, which requires oxygen and occurs at much lower temperatures, fusion is a nuclear process that takes place only under extreme conditions like those found in the sun's core. Every second, the sun fuses roughly 600 million tons of hydrogen into helium, producing energy that radiates outward through the solar interior and eventually escapes as light and heat. This energy powers Earth's climate, drives photosynthesis, and enables life itself. The fusion process is also incredibly stable. The balance between the outward pressure from fusion and the inward pull of gravity maintains the sun's shape and size. As the sun ages, the composition of its core will change, eventually leading to its transformation into a red giant and later a white dwarf. Understanding the nature of solar energy has been a triumph of modern physics, combining observational astronomy with nuclear theory. The sun serves as both a laboratory and a model for stars throughout the universe. It's not a flaming ball of fire, but a controlled nuclear furnace governed by the laws of quantum mechanics and thermodynamics. Water in space forms perfect floating spheres, no gravity to pull it down. In the microgravity environment of space, water behaves in ways that defy everyday expectations. On Earth, Gravity pulls water downward, forming puddles, rivers, and droplets that fall. But in space, the absence of gravity means water doesn't fall. It clumps together due to surface tension. This cohesive force between water molecules causes them to naturally pull into the shape with the smallest possible surface area, a sphere. When astronauts release water droplets aboard the International Space Station, the liquid forms perfect, floating balls that hover and drift. These spheres can range from tiny beads to blobs the size of a fist, and they adhere to surfaces, equipment, or even astronauts' faces. This property makes managing fluids in space a unique challenge. Specialized drinking containers and water systems are designed to control and direct the flow of water without relying on gravity. Surface tension becomes the dominant force in liquid behavior, influencing everything from how fluids are transferred to how medical procedures might be conducted in orbit. Scientists also study how microorganisms behave in water spheres, as the unique environment mimics certain aspects of cell behavior. These floating water spheres have become iconic images of life in microgravity and are not just a curiosity. They are essential to understanding how fluids work in spaceflight. They remind us that in space, even the simplest substances behave in unfamiliar and often mesmerizing ways. The behavior of water in orbit illustrates how gravity fundamentally shapes our world and what happens when that influence is removed. Enceladus, a moon of Saturn, has a subsurface ocean that could host life. Enceladus, one of Saturn's mid-sized moons, has become a prime candidate in the search for extraterrestrial life. Despite its relatively small size, only about 500 kilometers in diameter, Enceladus exhibits geological activity that hints at a liquid ocean beneath its icy crust. NASA's Cassini spacecraft provided the breakthrough in 2005 when it captured images of plumes of water vapor and ice particles erupting from fractures near the moon's south pole. These geysers shoot material hundreds of kilometers into space, suggesting a global ocean exists below a frozen shell, kept liquid by tidal heating caused by Saturn's gravitational pull. Analysis of the plume material revealed water, simple organic molecules, salts, and even traces of hydrogen gas, all ingredients potentially favorable for life. The presence of molecular hydrogen implies hydrothermal activity on the seafloor, similar to deep-sea vents on Earth, where life thrives without sunlight. These vents provide energy through chemical reactions, not photosynthesis, and host diverse ecosystems in Earth's oceans. If similar conditions exist on Enceladus, microbial life could be possible. What makes Enceladus particularly exciting is the accessibility of its subsurface ocean material. Unlike other ocean worlds like Europa, which are sealed beneath thick ice, Enceladus is actively ejecting internal material into space, allowing future missions to sample the ocean without drilling. This moon, once considered a frozen, unremarkable body, now stands at the forefront of astrobiology. Its active geology and chemical richness offer a tantalizing glimpse into the potential for life beyond Earth. In a vacuum, two pieces of metal fuse together, cold welding. In the vacuum of space, an unusual phenomenon occurs when two clean, flat pieces of metal come into contact. They bond together permanently without the need for heat or melting. This process is known as cold welding. On Earth, oxidation layers and contamination usually prevent metal surfaces from directly bonding. However, in the vacuum of space, where there's no atmosphere to deposit such layers, metal atoms on clean surfaces have no barrier between them. When these surfaces touch, the atoms don't recognize any distinction between the two objects. They effectively become one. Cold welding is a direct consequence of the atomic structure of metals and the absence of external molecules. Though it may sound like a rare laboratory occurrence, cold welding has real implications for spacecraft design and engineering. Unintended cold welding can cause moving parts like bearings, gears, or valves to seize, which poses a serious risk for satellites and space missions. Engineers mitigate this risk by using surface coatings, lubricants, or non-weldable materials in areas where metal-to-metal contact is unavoidable. The phenomenon was first recognized during early space missions and remains an essential consideration in modern aerospace engineering. Cold welding is not just a curiosity. It's an example of how everyday materials behave differently in the vacuum of space. It illustrates that outer space is not just an empty void, but an environment where physical laws manifest in new and often unexpected ways, requiring specialized solutions and deep understanding to ensure successful and safe mission operations. Solar wind is stripping Mars' atmosphere away even today. Mars, once potentially warm and wet, has become a cold and dry planet with a thin, unbreathable atmosphere. One of the primary reasons for this transformation is the solar wind, a constant stream of charged particles emitted by the sun. Unlike Earth, Mars lacks a global magnetic field to shield its atmosphere. As a result, the solar wind directly interacts with the upper layers of the Martian atmosphere, gradually eroding it over billions of years. NASA's MAVEN mission, Mars Atmosphere and Volatile Evolution, launched in 2013, has provided critical data on this process. MAVEN observed that during solar storms, atmospheric loss accelerates dramatically, with particles from the sun energizing atmospheric molecules and sending them into space. This stripping process is most intense at the poles and in the upper atmosphere, where ionized particles are particularly vulnerable. Over time, this loss has likely contributed to the disappearance of liquid water from the surface, as a thinner atmosphere cannot retain sufficient pressure or heat to support stable surface water. The remnants of Mars' magnetic field exist in localized crustal patches, offering limited protection, but they are insufficient to halt the overall loss. Understanding this mechanism helps scientists piece together Mars' climatic history and its shift from a potentially habitable environment to the arid world we see today. It also serves as a cautionary example of how planetary atmospheres can be lost and underscores the protective importance of Earth's magnetic field in sustaining our own life-supporting environment. Earth loses 100 tons of atmosphere to space every day. Every day, Earth loses approximately 100 tons of atmospheric particles to space, a process that, while seemingly large, is relatively minor in terms of Earth's total atmosphere. This loss happens primarily through several mechanisms: thermal escape, non-thermal escape, and interactions with the solar wind. Thermal escape involves light gases like hydrogen and helium, which gain enough kinetic energy to exceed Earth's escape velocity and drift into space. This is most common in the upper atmosphere, where solar radiation heats gases, giving individual molecules the speed to break free. Non-thermal escape processes include photoionization, charge exchange, and sputtering, all driven by interactions with solar radiation and the solar wind. These processes are more complex and often involve ionized particles being pushed out by electromagnetic forces. The Earth's magnetic field plays a critical role in minimizing atmospheric loss by deflecting solar wind particles and funneling some into the polar regions, where they create auroras. However, some charged particles can still strip atmospheric ions, especially during solar storms. Over billions of years, this slow but steady escape has subtly changed Earth's atmospheric composition. Despite the daily loss, Earth's gravity and magnetic shielding are strong enough to maintain a stable atmosphere over geological timescales. Understanding atmospheric escape is important not just for Earth, but for comparing planetary evolution across the solar system. It helps explain why Mars lost most of its atmosphere while Earth retained its own, and provides insights into how fragile a planet's habitability can be in the face of cosmic forces. Dead galaxies exist where no new stars are born. In the vast tapestry of the universe, not all galaxies are vibrant with stellar birth. Some galaxies, often referred to as dead or quiescent galaxies, have stopped forming new stars altogether. These galaxies are typically elliptical in shape and composed mostly of old, red stars, with little to no cold gas, the essential ingredient for star formation. Star formation ceases when a galaxy loses or exhausts its gas supply, or when conditions prevent the gas from cooling and condensing into new stars. Several processes can cause this shutdown. One major factor is feedback from active galactic nuclei, supermassive black holes at galactic centers that release immense energy as they consume matter. This energy can heat surrounding gas or expel it entirely, preventing it from collapsing to form stars. Galaxy mergers and environmental effects within galaxy clusters can also strip gas away or disrupt internal dynamics. Once a galaxy becomes quiescent, its stellar population ages, shifting its color to red as young, hot blue stars fade. Some dead galaxies stopped forming stars billions of years ago, shortly after the peak of cosmic star formation. Studying these galaxies helps astronomers understand the life cycles of galaxies and the forces that regulate star formation on cosmic scales. Despite their silence, dead galaxies hold vital clues to the past. They are fossil records of cosmic evolution. Their very stillness speaks volumes about the processes that can transform a galaxy from a bright, dynamic system into a cold, ancient archive of starlight. Black holes can evaporate. Hawking radiation. Black holes are typically seen as cosmic vacuums, regions of space-time so dense that nothing, not even light, can escape their gravitational pull. But in 1974, physicist Stephen Hawking introduced a revolutionary idea. Black holes can slowly evaporate by emitting radiation, a process now known as Hawking radiation. This phenomenon arises from quantum mechanics. In the vacuum of space, particle-antiparticle pairs constantly appear and annihilate each other. Near the event horizon of a black hole, if such a pair forms just right, one particle can fall in while the other escapes. The particle that escapes appears as radiation, while the one that falls in effectively reduces the mass of the black hole. Over immense timescales, this process causes the black hole to lose mass and eventually evaporate completely. For stellar mass or supermassive black holes, this evaporation is incredibly slow, taking longer than the current age of the universe. But for tiny hypothetical black holes, like those that might have formed in the early universe, Hawking radiation would be more rapid and possibly observable. The existence of Hawking radiation unites principles of quantum theory, general relativity, and thermodynamics, making it a cornerstone in the search for a unified theory of physics. Though it hasn't yet been observed directly, Hawking radiation remains one of the most significant theoretical predictions of modern physics. If confirmed, it would reshape our understanding of black holes, not as eternal traps of matter and energy, but as finite, dynamic objects with a life cycle that ultimately ends in disappearance. Time on the ISS runs 0.01 seconds faster per year, relativity in action. Time behaves differently in space. According to Einstein's theory of general and special relativity, the flow of time is affected by both velocity and gravity. On the International Space Station, ISS, astronauts experience time at a slightly different rate than people on Earth. Due to the station's high orbital speed, about 28,000 kilometers per hour, and its position in a weaker gravitational field than Earth's surface, time aboard the ISS actually ticks about 0.01 seconds faster per year compared to clocks on Earth. This is a manifestation of gravitational time dilation and special relativistic effects working in opposite directions. Special relativity says that moving clocks run slower, while general relativity says that clocks run faster in weaker gravity. In the case of the ISS, the gravitational effect dominates, so the net result is a slight gain in time. Though this difference is minuscule, it is measurable and has been confirmed by highly precise atomic clocks. These time discrepancies are not just theoretical curiosities, they have practical implications. GPS satellites, for example, must account for relativistic time shifts to maintain accurate positioning. Without such corrections, GPS errors would accumulate rapidly. The ISS serves as a real-world laboratory where these effects are not just calculated, but observed in action. The experience of time for astronauts diverges ever so slightly from that of people on Earth, offering a subtle but profound reminder that time is not absolute. It bends and stretches in response to speed and gravity. If we could see dark matter, the Milky Way would glow like a giant jellyfish. Dark matter is one of the most mysterious components of the universe. Though it does not emit, absorb, or reflect light, it exerts gravitational influence on visible matter and shapes the structure of galaxies. In the Milky Way, scientists estimate that dark matter outweighs ordinary matter by a factor of about 5 to 1. It forms an enormous halo surrounding the galactic disk, extending far beyond the visible stars. If we had the ability to see dark matter through some hypothetical form of vision sensitive to its distribution, the Milky Way would appear vastly different. Instead of a flat spiral, it would resemble a glowing, spherical jellyfish with long gravitational tentacles reaching out into the cosmic void. This image helps conceptualize how dark matter envelopes galaxies and governs their rotation. In fact, it was the anomalously fast rotation of stars in the outer regions of galaxies that led astronomers to infer the presence of dark matter in the first place. Without this invisible mass, galaxies would not have enough gravitational binding to hold themselves together at observed speeds. Although it doesn't interact electromagnetically, dark matter reveals itself through gravitational lensing, galaxy clustering, and cosmic microwave background measurements. Understanding it remains a major goal of astrophysics. Dark matter doesn't just surround galaxies. It sculpts the universe on the largest scales. If we could visualize its presence directly, the cosmos would take on an entirely new, almost ethereal form, revealing the hidden architecture that supports everything we see. The Moon is drifting away at 1.5 inches, 3.8 centimeters, per year. The Moon, Earth's only natural satellite, is slowly moving away from our planet at a rate of about 1.5 inches, or 3.8 centimeters, per year. This phenomenon is caused by tidal interactions between the Earth and Moon. As Earth rotates, its gravity pulls on the Moon, but the Moon also raises tidal bulges in Earth's oceans. These bulges are slightly ahead of the Moon's orbit due to Earth's faster rotation. The gravitational pull from these bulges exerts a forward force on the Moon, causing it to gain angular momentum and gradually move outward. Meanwhile, Earth's rotation is slowly decelerating, adding about 2.3 milliseconds to the length of each day every century. This process has been confirmed through laser ranging experiments, where retroreflectors placed on the Moon's surface by Apollo astronauts are targeted with lasers from Earth. The time it takes for the light to bounce back is measured with extreme precision, allowing scientists to calculate the Moon's distance. Over hundreds of millions of years, this drift has significantly changed Earth's relationship with the Moon. In the distant past, the Moon was much closer and appeared larger in the sky, while Earth days were significantly shorter. In the far future, the Moon's recession will eventually result in tidal locking, where Earth will also always show the same face to the Moon. The gradual separation illustrates the long-term dynamism of planetary systems, where gravitational interactions subtly reshape cosmic relationships across astronomical timescales. Jupiter is Earth's cosmic shield, sucking in dangerous asteroids. Jupiter, the largest planet in the solar system, plays a crucial role in protecting Earth from potential asteroid and comet impacts. Due to its immense mass, over 300 times that of Earth, Jupiter has a powerful gravitational field capable of altering the trajectories of objects passing through the solar system. Often referred to as a cosmic vacuum cleaner or gravitational shield, Jupiter attracts, deflects, or captures many comets and asteroids that might otherwise pose a threat to Earth. Its influence is particularly significant in the asteroid belt, where it helps prevent the formation of another planet by disrupting collisions and maintaining orbital resonances. Jupiter's protective effect was dramatically demonstrated in 1994 when fragments of comet Shoemaker-Levy 9 collided with Jupiter's atmosphere, producing massive explosions visible from Earth. Without Jupiter's presence, some of those fragments might have ended up on a collision course with the inner planets. Simulations of solar system dynamics show that without Jupiter, Earth would experience a much higher rate of catastrophic impacts, potentially affecting the development or survival of life. However, Jupiter's role is complex. It can also perturb objects from stable orbits and send them toward the inner solar system. Still, its net effect is largely beneficial. By absorbing or diverting high-speed space debris, Jupiter reduces the frequency of impact events on Earth. Its existence is a cosmic stroke of fortune, acting as a massive gravitational shield that has helped create a more stable and life-friendly environment for our planet. The Sun makes up 99.86% of the solar system's mass. The Sun is by far the most massive object in our solar system, accounting for approximately 99.86% of all the mass contained within it. This overwhelming dominance means that every planet, moon, asteroid, and comet together contribute less than 0.14% of the solar system's total mass. The Sun's mass, about 1.989 x 10 superscript 3 kilograms, provides the gravitational glue that holds the solar system together, keeping all the planets and objects in orbit. Without such immense mass, the solar system wouldn't exist in its current form. The Sun's core is the site of continuous nuclear fusion, where hydrogen atoms are fused into helium under extreme pressure and temperature, releasing enormous amounts of energy. This energy radiates outward and powers everything from the sunlight that reaches Earth to the solar wind that shapes the outer boundaries of the solar system. The Sun's mass also dictates its life cycle. Currently about halfway through its 10 billion-year main sequence phase, it will eventually expand into a red giant, consuming Mercury and Venus and possibly Earth, before shedding its outer layers and ending as a white dwarf. The Sun's gravitational influence extends far beyond Pluto, reaching into the distant Oort cloud, where trillions of icy bodies reside. Understanding the Sun's mass is essential not only for celestial mechanics, but also for modeling stellar evolution. It acts as the central engine and stabilizer of our solar neighborhood, dictating both the conditions for life on Earth and the dynamics of every object that orbits it. Space is silent. No sound waves can travel in a vacuum. Space, despite its often dramatic depictions in science fiction, is profoundly silent. That silence isn't just poetic, it's physical. Sound requires a medium to travel through, such as air, water, or solids. In the vacuum of space, there are so few particles per volume that pressure waves, the basis of sound, can't propagate. Without atoms or molecules to carry vibrations, sound as we know it simply doesn't exist. So, if you were to witness an explosion in space, you'd see it, but you wouldn't hear a thing. The intense silence of space was first directly experienced by astronauts, who described it as eerie and complete. Spacecraft, spacewalks, and even asteroid collisions all occur in total acoustic isolation. On Earth, even in the quietest environments, sound waves still travel through air or other materials. But in space, communication relies entirely on electromagnetic signals like radio waves, which don't need a medium and can travel through a vacuum. Inside spacecraft or space stations, sound can travel because they contain air. That's why astronauts can talk and hear inside. But outside the hull, only radios and other electronic communication methods function. Interestingly, while we can't hear events in space, we can convert other cosmic signals, such as radio waves, X-rays, and gravitational waves, into audible frequencies for analysis. So, while space remains physically silent, humanity has found ways to give it a voice through technology. That silence is one of the defining characteristics of the cosmos, an endless expanse without echoes. Betelgeuse could go supernova any day now. Betelgeuse, a massive red supergiant in the constellation Orion, is nearing the end of its stellar life. It's about 700 light-years from Earth and over 700 times the Sun's diameter. Given its mass and age, Betelgeuse is expected to end in a spectacular supernova explosion. While any day now, in astronomical terms, could mean tomorrow or tens of thousands of years from now, Betelgeuse is unquestionably in its final evolutionary stages. In late 2019 and early 2020, the star dimmed significantly, sparking speculation that it might be nearing collapse. While later research attributed this dimming to a dust cloud ejected from the star's surface, it reinforced interest in Betelgeuse as a supernova candidate. When it does explode, Betelgeuse will briefly outshine the full moon and be visible even during the day. The light show will last for weeks or months, though no danger is expected to Earth given its distance. Supernovae like the one Betelgeuse will occur when the star exhausts its nuclear fuel. The core collapses under gravity and then rebounds, ejecting outer layers in a massive explosion. This process enriches the surrounding space with heavy elements, essential for forming new stars and planets. Betelgeuse's supernova will provide a rare opportunity for scientists to observe such an event close-up, using modern telescopes and instruments. Its death will mark the end of a star that has fascinated humans for millennia, and at the same time, contribute to the cycle of cosmic renewal. A NASA spacesuit costs $12 million. A modern NASA spacesuit, officially called the Extravehicular Mobility Unit, EMU, costs an estimated $12 million to build. This astonishing figure reflects the immense complexity and precision engineering required to keep a human alive in the vacuum of space. The suit functions as a personal spacecraft, providing life support, protection, and mobility in one wearable system. Constructed from over a dozen layers of materials, the EMU shields astronauts from temperature extremes, ranging from -250 degrees Fahrenheit in shadow to +250 degrees Fahrenheit in sunlight, and from micrometeoroids traveling at high speeds. The suit includes a portable life support system, which controls oxygen, removes carbon dioxide, regulates humidity, and monitors body temperature. Its communication system allows astronauts to stay in constant contact with mission control, while the helmet visor protects against intense solar radiation and provides visibility. While the life support backpack alone costs millions, other components like the gloves are also critical, engineered for dexterity and durability in the harsh environment of space. Each suit is custom-fitted to the astronaut and regularly tested for performance. Despite the cost, most of the suits used today are decades old, originally developed for the Space Shuttle program. NASA is currently investing in next-generation suits for Artemis missions to the Moon and future Mars exploration, focusing on flexibility, modularity, and durability. The price tag of a spacesuit underscores the engineering challenges of surviving in space. It's not just clothing. It's a meticulously designed, life-preserving machine built for one of the most extreme environments known. Saturn's rings will disappear in 100 million years, falling into the planet. Saturn's iconic rings, easily visible even through small telescopes, are not permanent structures. They are composed mostly of ice particles, with some rock and dust, ranging in size from tiny grains to chunks the size of houses. These rings are incredibly wide, over 270,000 kilometers across, but surprisingly thin, often just 10 meters deep. Despite their grandeur, Saturn's rings are slowly vanishing. Observations by NASA's Cassini spacecraft revealed that the rings are being pulled into Saturn by its gravity in a process called ring-ring. This happens when ultraviolet light from the sun charges the ring particles, causing them to spiral along magnetic field lines and fall into the planet's atmosphere. Cassini estimated that Saturn loses about 10,000 kilograms of ring material per second. Based on current rates of loss, the entire ring system could disappear in roughly 100 million years, an instant in cosmic time. The rings may have formed relatively recently, possibly just a few 100 million years ago, from the breakup of a moon or icy body that strayed too close. That means we live in a rare window of time when Saturn's rings are visible. Future generations, millions of years from now, may look up at a ringless Saturn. Studying their composition, dynamics, and eventual disappearance gives scientists insights into planetary formation and evolution. Though temporary on a cosmic scale, Saturn's rings have shaped our perception of the planet and continue to offer a vivid example of both the beauty and impermanence of celestial phenomena. Mars has the tallest mountain, Olympus Mons, 13.6 miles per 21.9 kilometers high. Olympus Mons, located on Mars, holds the title of the tallest known mountain in the solar system. Towering approximately 21.9 kilometers, or 13.6 miles, above the Martian surface, It stands nearly 3 times the height of Mount Everest. Olympus Mons is a shield volcano characterized by its broad, gently sloping sides formed by repeated lava flows. Its base is about 600 kilometers wide, roughly equivalent to the size of the state of Arizona. The volcano's colossal size is made possible by Mars' low gravity, about 38% of Earth's, which allows structures to grow taller without collapsing under their own weight. Additionally, Mars lacks tectonic plate movement, meaning volcanic hotspots remain fixed beneath the surface, allowing a volcano to build up in one location for extended periods. Olympus Mons is estimated to be over 200 million years old, and evidence suggests it was active relatively recently in geological terms, possibly within the last few million years. The summit features a massive caldera, an enormous crater formed when the volcano's magma chamber emptied and collapsed inward. While currently dormant, Olympus Mons could erupt again in the future. Its scale challenges our understanding of planetary geology and has made it a prime location of interest in the search for ancient Martian life. The vast lava plains surrounding the mountain also offer a potential landing zone for future missions. Olympus Mons stands as a monument to the dynamic volcanic history of Mars and serves as a stark reminder of the planet's once fiery interior. Uranus rolls around the Sun like a barrel, 98 degrees axial tilt. Uranus is unique among the planets of the solar system due to its extreme axial tilt of about 98 degrees. This means that Uranus essentially rolls around the Sun on its side, with its rotational axis almost parallel to the plane of its orbit. The cause of this unusual orientation is believed to be a massive collision with a protoplanet-sized object early in Uranus history. The result is one of the strangest seasonal cycles in the solar system. Each pole experiences 42 years of continuous sunlight followed by 42 years of darkness as the planet completes its 84-year orbit around the Sun. This unusual tilt also affects the planet's magnetic field, which is misaligned with its rotational axis by about 60 degrees, leading to a highly asymmetric and dynamic magnetosphere. Despite being classified as a gas giant, Uranus is often referred to as an ice giant due to its composition, which includes water, ammonia, and methane ices. Its blue-green color comes from methane in the upper atmosphere, which absorbs red light and reflects blue. The sideways rotation also causes peculiar weather patterns and may contribute to the planet's low internal heat compared to its peers. Uranus' odd orientation makes it a fascinating object for scientists, and future missions are planned to explore it more closely. Its unusual axial tilt and resulting effects on magnetism, seasons, and climate make Uranus a unique case study in planetary dynamics and the long-term consequences of ancient cosmic impacts. Pluto is smaller than Russia. Though once considered the 9th planet of the solar system, Pluto was reclassified as a dwarf planet in 2006 due to its small size and orbital characteristics. Measuring about 2,377 kilometers, 1,477 miles, in diameter, Pluto is indeed smaller than Russia, which stretches over 6,000 miles from west to east. In fact, Pluto is only about 2/3 the size of Earth's moon. Despite its small size, Pluto has captivated astronomers and the public alike, especially after NASA's New Horizons spacecraft flew past it in 2015. The mission revealed a complex, geologically active world with towering ice mountains, vast nitrogen plains, and a thin but dynamic atmosphere composed primarily of nitrogen, with traces of methane and carbon monoxide. One of the most prominent surface features is Sputnik Planitia, a heart-shaped glacier of nitrogen ice, hinting at internal processes and possibly even a subsurface ocean. Pluto's orbit is also highly eccentric and inclined compared to the planets, occasionally bringing it closer to the Sun than Neptune. It has 5 known moons, the largest being Charon, which is so substantial in size relative to Pluto that the two bodies actually orbit a common center of mass located outside of Pluto itself. The revelation that Pluto is smaller than Russia emphasizes how diverse and surprising our solar system is. Though diminutive in scale, Pluto continues to teach scientists about planetary formation, icy bodies in the Kuiper Belt and the complexities of worlds far from the Sun. The ISS sees 16 sunrises and sunsets a day. The International Space Station, ISS, orbits Earth at a speed of approximately 28,000 kilometers per hour, 17,500 miles per hour, completing one full orbit roughly every 90 minutes. Because of this high orbital velocity, astronauts aboard the ISS witness 16 sunrises and 16 sunsets every Earth day. Each cycle of day and night lasts just 45 minutes, creating a rapid alternation between sunlight and darkness. The station orbits at an altitude of about 400 kilometers, 250 miles, above Earth's surface, within the thermosphere, where the thin atmosphere offers little resistance and excellent viewing conditions. From this vantage point, sunrises and sunsets appear dramatically different than on Earth. As the station crosses the terminator, the line dividing night from day, astronauts see the sun rising or setting through the thin curve of Earth's atmosphere, creating vibrant bands of color, deep reds, oranges, and blues that shift rapidly as the station moves. The constant cycle affects circadian rhythms, so the ISS uses artificial lighting and structured schedules to help astronauts maintain healthy sleep and work patterns. These frequent sunrises and sunsets are more than a visual spectacle. They also allow for regular calibration of instruments and Earth observation under varying lighting conditions. The phenomenon underscores the speed and precision with which the ISS orbits our planet, and it's a daily reminder for astronauts of their unique position in space, circling Earth so quickly that a full day's worth of sunrises and sunsets can be experienced before lunch. Sunlight takes 8 minutes to reach Earth. The light and warmth we receive from the sun do not arrive instantaneously. In fact, it takes about 8 minutes and 20 seconds for sunlight to travel from the sun's surface to Earth. This is because light, while incredibly fast, is still bound by the universal speed limit, approximately 299,792 kilometers per second, 186,282 miles per second. Given the average distance from the Earth to the Sun, about 149.6 million kilometers, 93 million miles, known as an astronomical unit, this travel time becomes a critical measure in astronomy and space science. When we look at the Sun, we're seeing it as it was over 8 minutes ago. This time lag also means that if the Sun were to suddenly go dark or explode, hypothetically, we wouldn't know until 8 minutes later. It's a powerful reminder that even light has limits and that space, vast as it is, stretches our concepts of immediacy. Interestingly, the light we see as sunlight actually takes much longer to travel from the sun's core, where it's generated by nuclear fusion, to the surface. Photons created in the core can take tens of thousands, or even hundreds of thousands, of years to reach the surface due to a process called radiative diffusion, where they are absorbed and re-emitted by particles in the sun's dense interior. Only once they escape the sun's surface do they speed across space at light speed. So, every time we step into sunlight, we're catching the end of a journey that started eons ago. Astronauts grow up to 2 inches, 5 centimeters, taller in space. In microgravity, the human body experiences changes that aren't possible under Earth's gravity. One of the more surprising effects is that astronauts can grow up to 2 inches, 5 centimeters, taller while living in space. This temporary height increase is due to the decompression of the spine in the absence of gravity. On Earth, gravity constantly compresses the vertebrae in our spines, keeping us at our usual height. In orbit, that compression disappears, and the cartilage discs between vertebrae expand, allowing the spine to stretch. This elongation doesn't affect bones themselves, but the spacing between them. The change is usually most pronounced within the first few days of a mission and tends to stabilize over time. However, upon return to Earth and the reintroduction of gravity, astronauts quickly revert to their original height. While this may sound like a minor inconvenience or even a fun side effect, it actually creates challenges. Space suits, for example, must account for these physical changes to ensure comfort and functionality during spacewalks. In some cases, back pain is reported, possibly due to spinal elongation or muscle weakening. This phenomenon highlights the remarkable adaptability of the human body in different gravitational environments and underscores the importance of monitoring musculoskeletal health in space. Studying these changes helps scientists prepare for long-duration missions, such as those to Mars, and informs how astronauts might cope with long-term effects of living and working in a low-gravity environment. Tears in space form floating blobs instead of falling. In the microgravity environment of space, even the most basic human experiences, like crying, are dramatically altered. On Earth, gravity pulls tears downward, allowing them to flow out of the eyes and down the cheeks. But in space, tears do not fall. Instead, they accumulate around the eye in small, cohesive blobs. This happens because the surface tension of water in a weightless environment causes liquids to stick together in spherical shapes. These floating tear blobs can cling to the eye and the skin around it, sometimes requiring astronauts to manually remove them or let them float away. The sensation can be uncomfortable and even blur vision if not dealt with. Crying in space becomes more than emotional. It's a unique physical experience dictated by physics. Even basic hygiene, such as washing the face or rinsing out the eyes, requires specially designed tools like no-rinse wipes or suction-based fluid management systems. This phenomenon extends beyond tears to all liquid behavior in space, including drinking, sweating, and even urinating. Water doesn't flow as it does on Earth. It clings, floats, and behaves in ways that challenge intuition. Studying how fluids behave in microgravity is essential for spacecraft design, life support systems, and astronaut health. NASA and other space agencies continuously test and refine equipment to manage fluid-related challenges during long-duration missions. The behavior of tears in space, while seemingly trivial, is a vivid illustration of how completely different even familiar human functions become beyond Earth's gravity. The Milky Way will collide with Andromeda in 5 billion years. In approximately 5 billion years, the Milky Way galaxy will collide with its nearest large neighbor, the Andromeda Galaxy, in an event astronomers call a galactic merger. This titanic interaction will be driven by the mutual gravitational attraction between the two galaxies, which are currently racing toward each other at about 110 kilometers per second, roughly 250,000 miles per hour. Although both galaxies are vast, each containing hundreds of billions of stars, the space between individual stars is so great that direct stellar collisions are unlikely. Instead, the merger will distort the shapes of both galaxies, flinging stars into new orbits and creating spectacular tidal tails of gas, dust, and stars. Over the course of billions of years, the galaxies will pass through each other several times before eventually coalescing into a single, more massive elliptical galaxy. Simulations suggest the final product will resemble the giant elliptical galaxies we see in the centers of galaxy clusters today. This cosmic event, though dramatic in scale, is not expected to endanger our solar system. However, it may be relocated to a different region within the new galaxy. By the time the merger occurs, the Sun will likely be in its red giant phase, possibly having engulfed Mercury, Venus, and even Earth. Thus, while the future collision represents a profound moment in galactic evolution, it is unlikely to be witnessed by humanity. Studying such interactions helps astronomers understand the life cycles of galaxies and the gravitational choreography of the universe. Astronauts can't burp in microgravity, no gas separation. In space, many everyday human functions behave in unfamiliar and sometimes uncomfortable ways. One of these is digestion. On Earth, gravity naturally separates the gases from the liquids and solids in our stomach, allowing us to burp safely when gas builds up. However, in microgravity, this separation doesn't occur. The result is that attempting to burp in space can lead to what astronauts refer to as a wet burp, where both gas and stomach contents are expelled together, essentially a small regurgitation. This happens because the buoyancy-driven rise of gas bubbles, which occurs on Earth, doesn't function in the same way in weightlessness. Gas remains mixed with liquids and solids in the stomach, meaning astronauts must be very cautious. This phenomenon highlights the broader challenges the human body faces in space. Without gravity, even fundamental systems like digestion are affected. Space agencies carefully design astronaut diets to minimize discomfort, including avoiding foods that produce excess gas or are too acidic. The inability to burp safely may seem minor, but it illustrates how Earth-dependent our physiology is. Everything from eating and sleeping to waste elimination becomes more complex in orbit. Understanding these effects helps mission planners optimize nutrition, design spacecraft life support systems, and prepare for longer voyages, such as missions to Mars. Even something as simple as a burp requires a reevaluation when gravity is removed from the equation, reminding us how finely tuned our biology is to life on Earth, and how adaptable it must become for life in space. Olympus Mons, Mars, is the solar system's largest volcano. Olympus Mons is the largest known volcano in the entire solar system, located on Mars. Towering at about 21.9 kilometers, 13.6 miles, in height, it stands nearly 3 times taller than Mount Everest and spans an area roughly the size of France. This immense shield volcano has gently sloping sides formed by repeated, slow-moving lava flows that allowed its mass to accumulate over millions of years. The Martian atmosphere and surface conditions are key to its enormity. Mars has lower gravity than Earth, about 38% of Earth's gravity, which allows volcanic structures to grow much taller before collapsing under their own weight. Also, Mars lacks plate tectonics, the movement of crustal plates, which on Earth distributes volcanic activity across different locations. On Mars, volcanic activity can remain concentrated in one spot for an extended time, enabling Olympus Mons to grow uninterrupted. The caldera, or summit crater, is about 80 kilometers, 50 miles, wide and contains multiple overlapping collapse features, indicating many episodes of volcanic activity. Though currently dormant, Olympus Mons may not be extinct, and there's evidence it was active within the last few million years, a short time geologically. Its relatively young lava flows and lack of cratering suggest the potential for future eruptions. Olympus Mons is more than a massive geological feature. It's a window into the volcanic history of Mars and a candidate site for future exploration. Understanding how such a volcano formed helps scientists refine theories about Mars' interior, thermal evolution, and potential for past habitability. Earth's water is older than the Sun, formed in interstellar space. Earth's water, the very substance that supports all known life, predates the formation of the Sun itself. Scientific analysis of isotopic ratios in ancient meteorites and comets, specifically the ratio of deuterium to hydrogen, shows that much of the water in our solar system originated in interstellar space. This means the water molecules formed in the cold, dense clouds of gas and dust that existed before the Sun ignited. Within these molecular clouds, ultraviolet light from nearby stars and cosmic rays triggered chemical reactions on the surfaces of dust grains, producing water ice. These grains, coated with frozen water, were then incorporated into the protoplanetary disk, the swirling material from which the Sun and planets eventually formed. As Earth coalesced from this disk, some of that primordial water became part of its composition, either through direct accretion of icy materials or by later impacts from water-rich bodies like asteroids and comets. This means that every glass of water we drink may contain hydrogen atoms that are over 4.5 billion years old, forged in the depths of ancient stellar nurseries. Understanding the ancient origin of Earth's water informs our theories about how habitable planets acquire their most essential resources. It also raises intriguing questions about the potential for water, and therefore life, elsewhere in the universe. If water formation is a common process in star-forming regions, then habitable conditions could be more widespread than we once believed, making Earth part of a broader cosmic pattern. Spacesuits can hit 250 degrees Fahrenheit, 120 degrees Celsius in sunlight. In the vacuum of space, environmental conditions can be extreme, especially regarding temperature. Without an atmosphere to diffuse or block solar radiation, Temperatures in direct sunlight can soar to 250 degrees Fahrenheit, 120 degrees Celsius, or more. A spacesuit is an astronaut's only protection against these conditions. It must shield the wearer from both intense heat and extreme cold, as temperatures can also plummet to minus 250 degrees Fahrenheit, minus 160 degrees Celsius in the shadowed regions. NASA's Extravehicular Mobility Unit, EMU, the standard suit for spacewalks, is a sophisticated life support system. It includes multiple layers: inner cooling garments that circulate water to regulate body temperature, and outer thermal micrometeoroid layers that reflect solar radiation and insulate against heat loss. The suit's visor has a thin gold coating that reflects sunlight, much like sunglasses, to prevent blinding glare and retinal damage. Thermal control is actively managed through a combination of insulation and temperature-regulating systems. This ensures that the suit's interior remains around room temperature, even as the exterior experiences boiling or freezing conditions. These design elements are critical for survival, not just comfort. A failure in thermal regulation can result in heat stroke, hypothermia, or equipment damage. Each suit is customized, rigorously tested, and costs approximately $12 million due to its complexity and life-preserving capabilities. The extremes experienced during extravehicular activities highlight the challenges of working in space and the technological ingenuity required to enable human presence in such a harsh environment. These conditions will be even more demanding on future missions to the Moon, Mars, and beyond. In space, there's no up or down. In the weightless environment of space, the familiar concepts of up and down lose all practical meaning. On Earth, gravity defines orientation. We stand upright, objects fall downward, and buildings have floors and ceilings. In space, however, there is no universal frame of reference. Astronauts aboard the International Space Station, ISS, for example, experience continuous freefall around Earth, creating a condition known as microgravity. In this state, every direction feels the same, and orientation becomes relative. Astronauts can work while upside down or sideways, and floors and ceilings are defined more by habit and utility than physical law. Tools are attached with Velcro or stowed in pockets to prevent them from drifting. Laptops may be mounted at odd angles, and labels on equipment are often printed in multiple orientations. Even basic activities like eating or writing can happen in any direction. This lack of gravitational bias requires mental adaptation. New arrivals to space often experience spatial disorientation until their brains adjust to the absence of a gravitational frame. The lack of up and down also impacts spacecraft design. Interiors are organized with accessibility and ergonomics in mind, not traditional floor plans. The disorienting nature of space orientation is a challenge, but also a fascinating insight into how deeply our senses depend on gravity. As humans venture farther into space, to the Moon, Mars, and possibly deep space habitats, understanding and adapting to a gravity-free orientation will remain a fundamental part of life and operations. The Moon is tidally locked. We only see one side. The Moon is tidally locked to Earth, meaning the same side of the Moon always faces our planet. This occurs because over time, Earth's gravity has gradually slowed the Moon's rotation to match the time it takes to orbit Earth, approximately 27.3 days. As a result, the Moon rotates once for every orbit it completes, keeping one hemisphere perpetually facing Earth while the other remains hidden from view. This far side of the Moon, often mistakenly called the dark side, receives just as much sunlight as the near side, but it was unseen until the Soviet Luna 3 spacecraft imaged it in 1959. Tidal locking is a natural outcome of gravitational interaction over time. Earth's gravity exerts tidal forces on the Moon, creating bulges. These bulges experience torque, gradually altering the Moon's rotation until it's synchronized with its orbit. Many other moons in the solar system are similarly locked to their parent planets. The side we see, the near side, is dominated by dark basalt plains called Maria, formed by ancient volcanic activity, while the far side has a thicker crust and more impact craters. This asymmetry remains an area of active scientific investigation. Tidal locking also has a stabilizing effect on the Moon's orbit and on Earth's axial tilt, helping regulate our planet's climate. Understanding the Moon's rotational dynamics not only enriches lunar science, but also helps explain broader gravitational mechanics in planetary systems. The locked gaze of the Moon has shaped mythologies, science, and culture for thousands of years. The Sun is white, not yellow. Earth's atmosphere makes it look yellow. Though the Sun appears yellow or orange when seen from Earth, it is actually white when viewed from space. This discrepancy arises due to the scattering of light by Earth's atmosphere. Sunlight contains all visible wavelengths, which together combine to produce white light. When sunlight enters our atmosphere, shorter wavelengths, blue and violet, are scattered in all directions by molecules and small particles in the air, a phenomenon known as Rayleigh scattering. This is the same effect that makes the sky appear blue. However, during the day, especially when the sun is low on the horizon, the light must pass through more of the atmosphere. This increased distance causes more blue and violet light to scatter away, leaving behind the longer red and yellow wavelengths, which gives the sun its warm hue. In space, where there's no atmosphere to filter and scatter sunlight, astronauts and spacecraft cameras record the sun as it truly is, a brilliant, intense white. This true color reflects its surface temperature of about 5,778 Kelvin, typical of a G-type main sequence star. The white light spectrum produced by the sun also provides the full range of wavelengths necessary for life on Earth, driving photosynthesis and regulating biological rhythms. Recognizing the sun's true color is more than a correction of perception. It highlights the role Earth's atmosphere plays in shaping how we experience the universe. Without our atmosphere, both the sky and the sun would look vastly different, starkly revealing the raw brilliance of solar radiation. You wouldn't explode in a vacuum, but you die in 90 seconds. Contrary to popular science fiction, a human exposed to the vacuum of space would not explode. However, the consequences are still rapidly fatal. In the absence of atmospheric pressure, the air in your lungs would rush out almost instantly if you didn't exhale beforehand. Holding your breath could cause your lungs to rupture due to the internal pressure. Once exposed, oxygen in the blood would begin to dissipate, leading to hypoxia, lack of oxygen to the brain, within 10 to 15 seconds. You would lose consciousness quickly, but death wouldn't be immediate. Bodily fluids, including saliva and moisture in your eyes, would begin to boil at body temperature due to the lack of pressure, a process known as ebulism. Skin and underlying tissue would swell, but the elasticity of the skin would prevent rupture. Temperature isn't the immediate issue. Heat transfer in a vacuum is slow, but the body would eventually cool through radiation. After about 90 seconds to 2 minutes, irreversible damage would occur due to lack of oxygen and decompression. NASA has tested human exposure to near-vacuum conditions through accidental depressurization incidents in test chambers. In one case, the subject lost consciousness in 14 seconds, but survived without permanent injury after rapid repressurization. This knowledge informs the strict safety protocols aboard spacecraft and space stations, where pressure suits and sealed environments are critical. The vacuum of space is not instantly lethal, but it is unforgiving, and even a short exposure is deadly without immediate rescue. Floating in space is easier than walking. In the microgravity environment of space, floating is the natural state of motion. Unlike walking on Earth, which requires muscular effort and balance to counteract gravity, floating in orbit requires virtually no energy. On the International Space Station, ISS, astronauts are in continuous freefall around Earth, creating a condition where they experience weightlessness. In this state, movement is governed by Newton's first law of motion. An object in motion stays in motion unless acted upon by an external force. As a result, astronauts propel themselves gently by pushing off walls or handrails. Once in motion, they continue floating until they encounter resistance. Walking, by contrast, demands constant muscular contraction, energy expenditure, and coordination with gravity. Floating simplifies motion but presents its own challenges. Without resistance, stopping or steering requires forethought. Fine motor control becomes essential, and even small movements can send an astronaut drifting. Tools, food, and personal items also float, and must be secured to prevent them from becoming hazards or getting lost. While floating may be effortless, long-term weightlessness has physiological effects. Muscles weaken, bones lose density, and the cardiovascular system adapts to the reduced need to fight gravity. Regular exercise on specially designed machines is required to maintain astronaut health. Floating also affects spatial orientation. Astronauts must mentally adjust to a three-dimensional environment without an up or down. Floating may seem like the ultimate freedom, but mastering it requires training and adaptation. Still, compared to walking under Earth's gravity, floating in space is physically far easier. You can see the Andromeda Galaxy with the naked eye. On a dark, moonless night far from city lights, it's possible to glimpse the Andromeda Galaxy with the unaided eye. Located about 2.5 million light-years away, Andromeda is the nearest large spiral galaxy to the Milky Way and the most distant object visible without optical aid. To the naked eye, it appears as a faint, diffuse smudge of light in the constellation Andromeda, best seen in the northern hemisphere's autumn sky. Despite its distance, Andromeda's immense size, over 220,000 light-years across, makes it appear relatively large in the sky, spanning an area equivalent to 6 full moons. It's home to an estimated 1 trillion stars, more than twice the number in the Milky Way. The light reaching Earth from Andromeda began its journey long before modern humans evolved, making it a literal glimpse into the ancient universe. Observing it connects us to the vast scale of cosmic time and distance. Andromeda and the Milky Way are on a slow collision course, moving toward each other at about 110 kilometers per second. In roughly 4 to 5 billion years, they will merge to form a single, larger elliptical galaxy. That cosmic event, though far in the future, is already written into the dynamics of the universe. Seeing Andromeda with the naked eye requires clear skies and patience, but it's a powerful reminder of our place in a much larger cosmos. It is both a window into the past and a preview of our galaxy's future. The first living creature in space was a dog, Laika. Laika, a stray dog from the streets of Moscow, became the first living creature to orbit Earth when the Soviet Union launched her aboard Sputnik 2 on November 3, 1957. Her mission marked a significant milestone in space exploration, as scientists sought to understand whether a living organism could survive the stresses of launch and the conditions of space. Laika's spacecraft was equipped with a life support system, sensors to monitor her vital signs, and limited thermal control. At the time, the technology did not allow for a safe return from orbit, so Laika's mission was always understood to be one way. Though initially reported to have survived for several days, later accounts revealed that Laika died within hours due to overheating caused by a failure in the thermal control system. Despite the tragic outcome, her flight provided valuable data on the biological effects of spaceflight, including information on heart rate, respiration, and stress responses. These findings helped inform the design of future missions involving living passengers, eventually leading to human spaceflight. Laika's legacy is complex. She is remembered both as a pioneer of the space age and as a symbol of the ethical dilemmas in scientific advancement. In 2008, Russia unveiled a monument in her honor near the site of her training facility. Laika's journey was brief, but her role in history endures. She paved the way for Yuri Gagarin, the first human in space, and every astronaut who has followed. Her story reminds us that progress often comes at a profound cost. NASA uses gold foil to insulate spacecraft. The thin, metallic sheets that cover many NASA spacecraft are often mistaken for pure gold, but they're actually layers of multi-layer insulation, MLI, and the golden appearance typically comes from aluminized captain or mylar with a vapor-deposited layer of gold or other metals. This high-performance insulation is used to protect spacecraft from the extreme thermal environment of space. Temperatures in orbit can swing hundreds of degrees depending on whether a surface is in sunlight or shadow, and without an atmosphere to moderate heat transfer, radiation becomes the dominant form of thermal exchange. Gold, with its high reflectivity and low emissivity, is highly effective at reflecting infrared radiation, helping to manage internal temperatures. MLI is made of dozens of layers of reflective materials separated by spacers, designed to trap heat and reduce energy transfer. This prevents sensitive onboard instruments from freezing or overheating and maintains stable temperatures for electronic systems, fuel lines, optics, and detectors. The golden foil not only provides thermal protection but also helps shield against micrometeoroid impacts and space radiation. Unlike thick metal armor, this lightweight solution minimizes payload mass while maximizing protection. From the Apollo lunar landers to modern satellites and deep space probes, MLI remains a standard feature. Its design principles reflect a critical balance in space engineering, minimizing weight while surviving an unforgiving environment. The shimmering gold seen on spacecraft is more than aesthetic. It's a vital element of survival in space, where even slight temperature imbalances can cause mission failure. Space junk travels at 17,500 miles per hour, 28,000 kilometers per hour. Space junk, or orbital debris, includes defunct satellites, spent rocket stages, fragments from explosions or collisions, and discarded tools from spacewalks. These objects orbit Earth at astonishing speeds, up to 17,500 miles per hour, or about 28,000 kilometers per hour. At that velocity, even a tiny fragment the size of a paint chip can cause significant damage to spacecraft or satellites. The danger lies not in the size of the debris, but in its kinetic energy, which increases with the square of velocity. A 1-gram object traveling at orbital speed carries the energy of a bullet fired from a high-powered rifle. With tens of thousands of trackable pieces and millions of smaller, untracked fragments orbiting Earth, the growing problem of space debris poses a serious risk to space operations. The International Space Station, for example, performs regular maneuvers to avoid potential collisions, and spacecraft are designed with shielding, like Whipple shields, to absorb impacts from small debris. Collisions in orbit, such as the 2009 crash between a defunct Russian satellite and an active U.S. Iridium satellite, generate thousands of new fragments, worsening the problem. The situation has raised concerns about the Kessler syndrome, a theoretical scenario where cascading collisions render Earth orbit unusable. Agencies like NASA, ESA, and private firms now track debris and develop technologies for mitigation and removal, including robotic arms, nets, and harpoons. Managing space junk is critical for the safety of satellites, astronauts, and future missions, as humanity's footprint in orbit continues to grow exponentially. Neil Armstrong's footprints on the moon will last millions of years. When Neil Armstrong stepped onto the moon on July 20th, 1969, he left behind more than just a historic legacy. He left physical footprints that are still there today. The moon lacks an atmosphere, wind, or liquid water, which means there are no natural weathering processes like erosion or rain to disturb surface marks. As a result, the impressions made by astronauts' boots, rover tracks, and even spacecraft landings remain almost perfectly preserved in the moon's fine regolith. These marks could potentially last for millions of years, altered only by external forces such as micrometeoroid impacts or the gradual effects of space weathering caused by solar radiation and cosmic rays. The regolith, made of crushed rock and dust from billions of years of meteorite impacts, holds impressions well due to its fine, cohesive texture. Because there's no tectonic activity to shift the ground and no atmospheric movement to erase them, the footprints are frozen in time. However, over long geological timescales, tiny impacts from micrometeorites may gradually erode the marks. Still, the process is incredibly slow, making it likely that these historic traces will outlast most structures on Earth. Future lunar missions may even encounter and study them as part of moon heritage preservation efforts. Armstrong's footprints represent more than a first step on another world. They're a snapshot of human achievement preserved in a silent, airless landscape, untouched since the moment they were made. As of today, they stand as the most enduring human marks beyond Earth.